Thanks for the introduction. As he mentioned, I'm a senior data scientist at Metis. So I've got to start off by giving a 1-minute commercial for Metis, after which we'll get into the talk, I promise. So Metis is a data science training company. So many of you may know us for doing boot camps, but we also do corporate training, so teaching companies' employees data science. And we're the only accredited data science boot camp. So an outside organization comes and looks at us and makes sure our grads are actually getting jobs and having professional success. So I'm here representing them. So the real reason I'm here is, like many of you, I've seen that neural nets and deep learning are an extremely hot topic in data science. They're sort of changing a lot of what it even means to be a data scientist and do data science. But when you dig in and try to learn about these things, you can find lots of tutorials on how to implement models in Keras or TensorFlow and just use libraries to, do some magic things under the hood and produce some really cool results. And that's great, and for a lot of people, that might be all they need. But I was really interested in what's actually going on under the hood and what is the math that actually makes neural nets work. And so that's why I've started putting together talks like this one. So I'm really happy to be here and share this one with you. And my hope is that everybody comes away with a little bit of a better mental model for what neural nets are and how they work and why they work. And thanks for sticking around. Last talk of the day. Appreciate it. All right. There we go. Looks like I've got to zoom out a little bit. Okay. So my resolution's a bit smaller than I'd hoped. Let's just get this set up. All right. All right, I think this should work. Okay, so to begin, we want to do neural nets, right? So the first thing we've got to do is import TensorFlow, right? Nah, let's not do that. Let's do it from scratch. All right. So what are we going to do in this talk? We're going to do a few things, and I'll try to get the resolution right here. Zoom out a little bit. There we go. We'll implement a neural net with one hidden layer completely from scratch, and we'll use mathematical principles to get the back propagation right, to get the weights actually updating in the right way so that they can learn something. And that'll be the first part. The second part is we'll transition to deep learning. So we'll change our mental model of neural nets, not just to be pure math, but to understand them in terms of layers that are passing data between them, passing information forward and passing gradients backwards so that they can learn. Yeah, I'm trying to see how I can make it bigger without having it get cut off on the screen. Maybe I have to close my, there we go. Good call. There we go. All right, thank you. Okay, and then we'll show that this framework sort of built completely from scratch just from mathematical principles that may or may not even look like a neural net to many of you can actually learn MNIST. Okay, so we've all seen diagrams like this in the context of neural nets, sort of circles with arrows going between them, and that's supposedly what a neural net is. It's like a bunch of things that are interconnected. And some of us, because we might have gone to grad school or something, understand what's going on in that diagram, but most of us don't. And we just sort of trust that it does a sort of magical thing that, that can solve complicated computer vision problems or other kinds of problems. So this talk will attempt to fill that gap. So why do we even need neural nets in the first place? Let's start with that. Let's suppose that we have a function that has some complicated relationship between inputs and outputs. So let's say that we have some data that looks like this. And all this code will be on GitHub available. Feel free to live code along if you want. The code's actually not going to be too extensive. But yeah, it'll be on GitHub. So let's say our data looks like that. Let's say we have 3 features. simple sort of machine learning binary classification problem, randomly generated features, either ones or zeros, and our output is also just randomly generated, either ones or zeros. So I claim that a neural net could learn this relationship between inputs and outputs. We have 8 observations and some complex relationship between inputs and outputs. So first of all, so what is a neural net? So what do we want to learn here? We want to learn a function, mathematically, a function that takes in 3 variables and appropriately maps those variables to their outputs. It takes in, x1, x2, and x3 and produces the correct value of y. Well, first of all, why do we need something more complicated than just a traditional stats technique like logistic regression? Well, many of you have probably seen this before, but this is not a linearly separable problem, right? If you randomly generate this data, this is a 3-dimensional version of the XOR problem that's often shown in this context, but you can't just draw a line in 3-dimensional space that separates these points into all the ones on one side of the line, or a hyperplane in the case of 3 dimensions, and all the zeros on the other side. So this is the same reason why you can't use logistic regression to learn XOR. It's just not a linearly separable problem. All right, so we're going to try to build a little simple neural net that learns this instead. Well, actually, I'll say this. What our neural net's going to end up doing is it's going to end up learning hidden features that actually encode the information that lets us get from this complicated input to this output. We could instead figure out what those intermediate features are manually. We could do feature engineering. We could find combinations of our input features that allow us to predict our output. That's what a lot of cutting-edge machine learning research was before neural nets, especially in computer vision. But, of course, who likes feature engineering? Let's have the computer do the feature engineering for us via a neural network. OK, so what are we going to do? Our goal is, let's go back one. Our goal is going to be to start with our 3 original features, and we're going to do all this step by step manually so you can see exactly what's going on. We're going to start with our 3 original features. We're going to transform them into 4 intermediate or hidden features. And then we're going to use those 4 intermediate or hidden features and predict our output. And we're going to kind of hope that if we think about the math correctly, that all the parameters that are defining what those hidden features are actually get updated so that this neural net can learn this complex relationship. So we'll code up a bunch of equations, and it will turn out to essentially do the same thing as a neural net. All right, so here we go. Now I'm going to go through this step by step. There's going to be a lot of equations thrown up there. Each one of these equations is pretty simple, but there's going to be a lot of them. So I'm going to kind of speed through this, and I'll trust that if you want to go through and understand every detail of every equation, you can go look at this notebook. It's already on GitHub. I sent it to the organizers, so they should have sent it out to you. Well, if they didn't, I see a guy shaking his head. You can email me, and I'll send it to you. But the point is, what? Oh yeah, I'll put the link up. I'll put it up at the end of the talk. We should have time at the end. You want it right now? I wish there was a okay. Yeah, why not? What's up? No, I have the link right here. Let's see. I can just open the link real quick. It's GitHub, Seth H. Weidman, ODSC Neural Nets 11.14.17. I'll leave that up there for a minute. Yeah, we've got time. Yeah, that's all. Oh, and actually, you have to click on the ODSC Deep Learning 2017 notebook. There it is. It doesn't have all the cool transitions when you view it online, but that's what you get for trying to view it online. All right, let's go back to the presentation. I think everyone who's wanted to look at the link has looked at it by now. All right, so now let's go through actually doing a neural net step by step. Step one, we want to feed our original features, our x1, x2, and x3, into this intermediate layer. How do we want to do that? How do we want to transform our original features into some intermediate features? Well, we want 4 intermediate features, and I'll sort of call the steps of this neural net A, B, and C, and then the prediction that we end up making will be P. So the first layer of our neural net has 4 intermediate features, A1, A2, A3, and A4. And we want each one of those features to be sort of a linear combination of our original features, defined by some, or transformed by some weights that I'll call V. So for example, the first feature will just be a linear combination of our original features. So if we express our original data as just a vector, which is an intuitive thing to do, because if you think of a row of data, we typically think of that as a vector. And so to transform this into our intermediate features, we're going to multiply it by a matrix. Now again, there's lots of matrix multiplications that go on in neural nets, but those are only a means to the end of expressing the fact that you want these intermediate features that are linear combinations of your original features. It's just a concise way of expressing that idea. That's what we actually want. We want these intermediate features that are linear combinations of our original features. So coding that up, I'm just going to make my original data a 1x3 matrix, 1 row by 3 columns. I'm going to define a little weight matrix that's 3 rows by 4 columns. And then I'm going to just do the matrix multiplication of those in NumPy. There it is, zoomed in a little bit. All right. So where are we in terms of our neural net? We've gone from our original first layer and sort of gone into the hidden layer, into the intermediate layer. All right, what's next? Well, then we're going to, so neural nets are ultimately compositions of functions. They're mathematical functions that are composed together. The input of one, the output of one layer becomes the input to the next function. In order for this function to be nonlinear, in order for it to learn complex relationships between inputs and outputs, we have to feed it through a nonlinear function. So you sort of alternate these linear transformations, which are matrix multiplications, with nonlinear transformations, which we call activation functions, because original neural nets were sort of loosely modeled on the brain. So here, we're going to use an easy-to-understand activation function, the sigmoid function. Just 1 over 1 plus e to the negative x. Maps small numbers to 0, maps big numbers to 1, and maps numbers in between. It maps 0, in fact, to 0.5. So it's just a nonlinear function that we're going to apply to our data. OK, so to move forward in the neural net, since we have a vector now of 4 intermediate features, we're just going to apply sigmoid to every one of those intermediate features. And if we feed those through this activation function, it's just as simple as this. There's our sigmoid function. And we get a little vector that's the same dimensions as A, now called B, that is just the sigmoid of all the values in A. All right. So now we want to use these features as a linear combination to predict our final output. That's going to be the next step in our neural net. How do we do that? Well, just like we did linear combinations before, we define a little weight matrix that we're going to multiply our features by in a linear combination. And the final number that we're going to feed into another sigmoid function to get a prediction is going to be this number c. And it's just going to be a linear combination of the weights with our intermediate features. So that's equivalent to doing a matrix multiplication, or multiplying 2 vectors in this case, since we're only using a batch size of 1. And if you want to code this up, we'll define our little W matrix. And print out C there. And C is just a number. And where are we? We are now here. We've gone into the intermediate layer, fed it through a sigmoid function, and now we've gotten a number C. That's the thing we're going to feed into our final sigmoid. All right, so mathematically, what do we want? We want a prediction that's a sigmoid of C. So coding that up is really easy. Just feed C into the sigmoid function. And now, what have we done? We've gotten all the way to the end and made a final prediction. We've actually made a prediction with our neural net. And now we compute the loss. So we'll compute mean squared error loss, very simple. We don't want to penalize our we want to treat predictions that are too low or too high equally. A simple way to do that is to use mean squared error loss. And so that's really just squared error loss. And so that's what we're doing here. And we get this number L that represents our loss. It represents how much our neural net missed by. Okay. There we go. So now what? Now is where we really get to the secret sauce, the why of why neural nets work. So we've made a prediction using this neural net, using a bunch of weights that in our case were randomly initialized. So now what do we do? Now how do we, what do we do with that? We've missed by some amount. Our neural net's not very good. What do we do with that? Well, recall each step in our neural net was just a function that was applied to some input and resulted in some output. So you could write the neural net that we just did, not in terms of a diagram with circles and arrows, but as a series of mathematical functions. We started out with x, and we had this v thing added in there, and we got some number a. We fed that through another function. We fed this b through another function, etc., until we got our loss. That's another way of looking at the same thing that neural nets do. So if we have a neural net with just one hidden layer, you could write the loss explicitly as this. You could write it as just a big mathematical function that takes in both your input, x, and your two weight matrices, v and w, at certain points in that function. Well, once you think of neural nets as functions in that way, and actually in this case functions that we can explicitly write down, we know sort of how we want to update our weights. We know how we want to teach how we want the neural net to learn. It turns out we want it to learn according to these equations. We want to compute the partial derivative of the loss with respect to each of the weights, and then update the weights accordingly. Now, why does this make sense? Well, if you think about it, let's say that for a given weight, let's imagine an individual weight in that matrix W. If that weight is a positive number, if the partial derivative of the loss with respect to that weight is a positive number, that means that increasing the weight is increasing our loss. Well, that's bad. That means we want to decrease that weight. And so that's exactly what that equation does. W subtracts that positive partial derivative, so that weight will go down. If you think about the opposite scenario, where increasing that weight decreases our loss, that's great. That means we want to keep increasing that weight as much as we can. And so in that case, you'll be the equation W minus that partial derivative will be subtracting a negative number, and so you'll be increasing that weight. And so these are the equations that we want to use to update our weights. All right, so how do we actually compute these partial derivatives? That's going to involve a lot of math, it seems like. Well, we want to compute those two partial derivatives, and we know that this function, L, can be represented like this. So to compute the partial derivative, does anyone know what's coming next? What trick are we going to have to use from calculus in order to compute those partial derivatives? Scream it out if you know it. Anyone? Chain rule, exactly. We use the chain rule. Our good friend the chain rule tells us that this partial derivative is going to be these three partial derivatives multiplied together, and this one is going to be these 5 derivatives multiplied together. And this is how neural nets actually learn. All the matrix multiplications and all the things that go on in the back propagation pass of neural nets are to make everything line up so that all the weights in each of those matrices are updated in the correct direction. So that if increasing a weight increases the loss in the neural net, we decrease it, and vice versa. And so here we're going to actually compute these partial derivatives explicitly. And each one of these, for the most part, turns out to be pretty simple. So again, I'm going to go through this quickly and sort of go through all the math and show that you can compute these partial derivatives, you can multiply this stuff together and show that it works. If you want to check out all the details and everything, feel free to read the notebook or come up to me. I think we should have time at the end. But yeah, I'm going to sort of run through this. So step 1 of backpropagation. We want to compute the partial derivative of our loss with respect to the prediction. Okay, well, our loss was just that. And so the partial derivative of that with respect to p is just negative y minus p, as it turns out. And so coding that up is just that. There's our first partial derivative. Just negative y minus p. Yeah, there we go. I'll just kind of zoom in quickly so you can see it. Good, thanks for, yeah, if you want it to be bigger, keep yelling out. I'll try to zoom in when there's code up. All right, so that's the first thing we've done. We've gone backwards one step in our backpropagation. All right. Now let's compute this next partial derivative. So what was this partial derivative? Or what was this original function? Remember, this function was just a sigmoid function, this thing that passed, that transformed C, the linear combination of our hidden features, into our prediction. We just passed it through the sigmoid function. So the partial derivative of that with respect to C depends on the sigmoid function, and it turns out the sigmoid function has this nice property. If that's the sigmoid function there, 1 over 1 plus e to the negative x, some of you may know this, the derivative of that with respect to x turns out to be, or can be written as, the sigmoid of x times 1 minus the sigmoid of x. Makes coding things up pretty easy. Because indeed, so yeah, so that we can apply that rule to this function here. And indeed, that makes things pretty easy to code up. The partial derivative of p with respect to c is just the sigmoid of c times 1 minus the sigmoid of c. And so we get some number. All right. Where are we? We've gone backwards one more step, just to orient everybody. All right. Here we go. Next, we want to compute, actually, we have our weights. We have our second set of weights, w. And we want to figure out how much each of these weights influences the final prediction. And this turns out to be kind of cool. I just learned earlier today from Joel Gruss that there's a linear algebra theorem, more generally, that makes what I'm about to show true. But I'm just going to show the very simple version in when the matrix you're dealing with is 4 by 1. So the cool thing is this. Remember, C is a linear combination of the intermediate features with our weights W. So it's this quantity here. So we're trying to compute the partial derivative of that with respect to each of those weights. All right? However, the partial derivative of that with respect to each of those weights, so what is that? That's the partial derivative of C with respect to W11, with respect to this weight, with respect to this weight, et cetera. But what is that? Well, the partial derivative of C with respect to each of those weights, let me go back one. The partial derivative of this quantity with respect to the first weight is just this value B1, because the partial derivative with respect to all these others is 0. And the partial derivative of C with respect to the second weight is just B2, et cetera. So, as it turns out, the partial derivative of C with respect to W is just B transpose. Because of this, they turn out to just be B1, B2, B3, and B4. And we can code that up as just that. And we get a 4 by 1 matrix. And notice that this has the same dimensions as W, which is what we want. So now we can actually compute, again, explicitly, what is the partial derivative of the loss with respect to W. So what does this mean? This means for every one of those weights, W, how much does increasing or decreasing that weight change our loss? And we're ultimately just going to want to change the weight matrix by the opposite of that amount. And this has the same dimensions as W. So this is exactly what we want. All right. So continuing to move backwards, so we just computed this. The partial derivative of C with respect to W turned out to be B transpose. And can anybody see? The next thing we're going to compute is the partial derivative of C with respect to B. So with respect to B1, B2, B3, and B4. Well, what's that going to be? W transpose. Yeah. It's going to be essentially by the exact same logic we just went through. It's going to be W transpose. because the partial derivative with respect to v1 is this weight, the partial derivative with respect to v2 is this weight, etc. Again, the point is that we're figuring out how much we need to adjust these weights explicitly using calculus in order to change the loss. And that's really the secret sauce of why neural nets work. Coding this up is easy. That array print is a helper function that's on GitHub that you can check out, but it's not built into Python or anything, just so you know. All right, where are we? Well, we've kept going backwards, so now we're there. I'll go a little more quickly through the last couple of steps. Next, we're just going to compute the partial derivative of b with respect to a, and this turns out this is the same as this is also a sigmoid. So it turns out this is just the answer here is it's sigmoid of a times 1 minus sigmoid of a because of the derivative of the sigmoid function. And that's that. All right. Now this last one, the last one turns out to have a lot of steps because V is a 3x4 matrix. Going through all the steps and explaining why the partial derivative ends up being what it is takes a lot of explanation. So I'll mostly gloss through it, but I'll say that the end result ends up being the same as what we found before. The end result ends up being it's actually just X transpose. So the derivative of A with respect to V is X transpose, just like before. The partial derivative of C with respect to W was B transpose. And there's actually a linear algebra theorem that makes this all true. But if you want to go through all this painstaking stuff and see exactly why this works, I encourage you to do it. That's why I wrote it. But for the purposes of getting to the interesting stuff here, I'll let you go through this. Basically, it's the same logic. When you're computing these partial derivatives of the output with respect to the weights, each input only is multiplied by like one weight to get to the output. So the whole derivative ends up looking like this. There's basically an x1 here, an x1 here, an x1 here, an x1 here, x2, 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 x3, etc. And so to do the matrix multiplication to get all the weight updates to line up in the right way, you can just multiply by X transpose. Because remember, our original data was a row, and each one of those were columns. So that's why we're multiplying by X transpose. All right. Now we're getting close to the interesting part. Or, you know, that's the part that explains why it works. Let's actually see that it works. We've gone all the way back. So we've back propagated manually, step by step, the loss of our neural net through the entire network and figured out how to update each of our weights. Oh, and we have to compute explicitly the actual amount that V gets updated by. And again, remember, the partial derivative of the loss with respect to V was the product of these 5 partial derivatives. And it turns out to get everything to line up right, you do all the dot products of these and you get that. It's interesting because in our case, 2 of our features were actually 0. A lot of the weight updates in our case are actually 0 because of the way the matrix multiplication works out. But that's a side note. And this has the same shape as V. So this is actually the exact amount that we want to update V by. And now we'll actually update our weights. It's this simple. So W, we're going to subtract off the partial derivative of the loss with respect to W, and same for V. Yeah.
So you are just subtracting the derivative. You are not really learning the.
Yeah, we're going to get to that later. Yep, good question. All right, now this is basically a neural net. We're going to use this exact same function to learn MNIST in a second, but this is the forward pass. This is computing the loss, and this is back propagating that loss through the net like we just did. And this is updating the weights. And that's the sort of most concise way I know of to actually write a neural net. Well, we're going to do it in a second using classes, but in terms of just writing out step by step what's going on, that's how you do it. All right, let's look at some results. So let's say I'm going to do this. I'm going to take my data x and y, those 8 lines of x and those 8 ones and zeros of y. So remember, x was just randomly chosen, ones and zeros, 3 features, and y was just randomly chosen ones and zeros for the output. I'm going to run this through a neural net with 4 hidden neurons, like the one we just went through, and I'm going to do it 500 times. I'm going to do it for 500 epochs. What's an epoch? An epoch is running each observation through the neural net once. So I'm going to run all 8 observations through the neural net once. That's 1 epoch. Run all 8 through again. That's 2 epochs, etc. So I'm going to do that 500 times. And then we're going to look at how accurate it is. All right, so this is the result. So on the first epoch, the loss, the total mean squared error on the whole data set was this. And you can see that it goes down pretty quickly as the epochs go on. And these are the actual predictions that this neural net outputs, so the values of p that it outputs after being trained for 500 epochs. And you can see that it does pretty well. When it should predict 0, it does. And when it should predict 1, it does. So actually, just doing all this math and understanding the math of how the weights are supposed to get updated, it actually works. Well, at least it works on this toy example, right? 8 data points. The inputs are only ones and zeros. The outputs are only ones and zeros. That's sort of you might think, well, maybe that won't work on a more complex problem. So let's see if this neural net can learn MNIST. So what is MNIST, right? Who here knows what the MNIST data set is? Okay, almost everybody. I won't even talk about it then. Let's show that this can learn MNIST. All right, let's import some stuff. Let's get the data. And let's do a train test split. I'm going to put 90% of the data in my training set randomly, 10% in my testing set. I'll tell a funny story, actually, because I'm using sklearn here. I sat down at a table for breakfast on Thursday morning, and I was like, hey, can I sit with you guys? 2 guys are sitting there. And one of the guys goes, hey, I'm Andy. And I was like, okay, hi, Andy, whatever. And then I looked at his name tag, and his first name was Andreas. And then I realized it was Andreas Mueller, the creator of scikit-learn. So that was an awesome starstruck moment. So thank you to Andreas, if he's listening somewhere, for writing the train test split function. OK. I might have forgotten to run a cell there, so this might not work. All right, so let's actually see what happens. So we're going to run this just for 1 epoch. So I'm running. So before, we had a neural net. We coded up these equations with 3 inputs, 4 hidden neurons, and 1 output. Now we're going to do the exact same thing, except for MNIST, the images are 28 by 28. So we're going to have 784 inputs. Each input is going to, I've scaled it, so each input will have a value between 0 and 1. By default, the values are between 0 and 255 based on the darkness of the pixels, but I've scaled it so they're between 0 and 1. And we're going to have 50 hidden neurons. Just did some testing, and 50 turned out to work pretty well. And 10 outputs. It's going to output the probability of it being 0, 1, 2, 3, 4, etc. But the actual calculations that are going on are exactly what you saw me write explicitly. I'm not importing anything from outside of what you've already seen. Let's see. So just 1 epoch. So 10% would be random guessing. Yeah, 93%. So it works. You can just do neural nets from sort of mathematical first principles, just by seeing how the weights should be updated. We're not using any convolutions here. We're not using any dropout. We're not using any tricks. This is solving a sort of simple, classic computer vision problem using just mathematical first principles type reasoning. Again, just 1 epoch. So that's kind of cool. All right. But what are we all here for? We're all here to see how we can do deep learning. And it turns out deep learning, to get to deep learning, which is just neural nets with more than one hidden layer, you just take the stuff that has already been written and sort of get like, well, I'll just show you. So, okay, we just coded up a neural net with one hidden layer. That took about 20 or 25 steps. To do every step, to go for the forward pass, the loss, and the backward pass, updating the weights, it's about 20 or 25 lines of code to do a neural net with one hidden layer if you wrote every step out explicitly. So clearly, I wouldn't want to do that with deep learning. So notice there was some repeating of steps in there. So multiple times, we passed something through a sigmoid function, or we did a matrix multiplication and then passed something through a sigmoid function. And on the back propagation, as you saw, there were multiple times when we passed something through the derivative of the sigmoid function and then passed it backwards through another matrix multiplication. So there's some repeating of stuff in there. So basically, to go from what we just did to deep learning, now that we understand the math and why the equations are coded the way they are, we just need to get rid of some of that duplication of code and encapsulate things in classes a little bit. That's really all it is. So here's sort of what's going on at each point in the net. Zoom in there. Basically, you have input to the neuron that's coming from a weight matrix and the layer prior. And this is being fed through an activation function. And then on the back propagation steps, which are sort of in red, you sort of need to multiply things by the derivative of the activation function evaluated at the neuron input. And then for the next step, you need to do the transpose of the weight matrix. You basically need to multiply this by the transpose of the weight matrix. If you look back at sort of how we did those equations and reason through, like, okay, this is why it has to be the way it is, that's really what was going on. We were doing that multiple times. This operation is happening at each neuron in each layer. So there's some repetition here, and we can encapsulate this. So we can think of, so the way we're going to do this is we're going to code up neural nets as a class. And each neural net is going to have a list of layers as a class attribute. And the layers are going to be doing the work of sending things forwards and backwards and coding up the equations that we just went over. So we're sort of going to define our layers. And then the neural net will just take in a list of layers. All right. So neural nets, so one way to think of neural nets is just as a mathematical function. It just takes in inputs, does a bunch of transformations to it, and outputs something. You can also think of it sort of equivalently, and in some cases it's helpful to think of it in one way, and in some cases the other way. You can also think of it as a series of layers that pass sort of inputs or information forwards and pass gradients backwards. And that's sort of the mental model we're going to have for the second part of this. What time is it? 4:12. All right, let's show how to do this. Oh yeah, I am indebted to this guy. I said that I haven't been able to find a lot of great tutorials online on this stuff. This guy, I don't know, maybe this guy's chuckling, maybe he knows this guy. This guy's GitHub is absolutely phenomenal. He has a ton of great stuff on there. I encourage you to check it out. I looked up to see, like, he was a student at some university in Denmark. Yes, definitely take your phones out and take a picture of this slide. He was some student at a university in Denmark, and he was making tons of commits on GitHub, and then he stopped in early 2017. And he stopped publishing papers, and I was like, what happened? Why did he stop? And I looked up his LinkedIn, and he now works at Apple as a machine learning engineer. So they got him. Yeah, whoops. Anyway, all right. So first, this is just a helper function that I'm going to use throughout to set up layers in the neural net. And all it's going to do is, so the way I'm going to define my neural net is I'm going to have a list of all the hidden layers that are just going to have the number of neurons in that hidden layer. So if I had a list of 50, 40, 30, 20, 10, that would mean first layer, 50 hidden neurons, second layer, 40 hidden neurons, third layer, 30, et cetera. And then I have the number of outputs that I have. And so so actually, if I was doing this not in a Jupyter notebook in Rise as part of a presentation, this would just be a class method within the neural net class, but that would take up too much room on the screen. So I'm having this as a separate function, a global function that I'm calling instead. This is just a little helper function that sets up the layers. All right, so let's look at what a neural net is. All right, so what do we got here? Well, a neural net is going to have a certain number of hidden neurons in each layer. It's going to have outputs here. It's going to have a loss function. And when we initialize it, it is not going to have its layers set up. The forward pass through a neural net, well, if we haven't set up the layers yet, we first need to set up all the layers, and then we'll set that equal to true. And then, and this is sort of the clever, and this is the way a few people that have done this do this. I don't claim this part is actually like from other people's work. This part is not original. Basically, to feed data forward through the neural net, you just have each layer do a forward propagation step. You have the layer send the data to the next layer. And you end up, the last layer, the result of it, is your prediction. And then you return that as the result of the forward pass function. Calculating the loss, you just take the prediction and whatever your y is, and you compute the loss based on your loss function. And the back propagate function does sort of a similar thing. It takes the loss as its first step and sends the loss backwards through the neural net. So it does the back propagate step with each layer. So let's make sure we run that cell. All right. Now what is a layer? Well, it has to have a forward propagate and a back propagate step, class method. And for a fully connected layer, we'll just try to code up the equations that we already reasoned through have to be the way that neural nets learn. We'll try to code those up into our layers, into our forward prop and back prop functions. And there's some terminology. It's not easy to code this all up and make it easy to follow. So there's some terminology here. We'll say like Li is our layer input. The activation input, the thing that goes into the circle, is AI, and then the activation output is that, and the layer gradient, the thing that gets passed backward through the neural net, is LG. And so that's what it ends up looking like. Let me go back. All right. So what do we have for a fully connected layer? Well, it has a certain number of neurons, right? It's got an activation function, and we'll only do sigmoid in this talk, but actually further on in the talk, but after I don't think we'll have time in the 90 minutes, I show how you can do other activation functions. Not too bad. We have a number of iterations in case you want to do learning rate decay or anything like that. And initially, we haven't initialized the weights. For forward propagation, it's actually pretty easy. The layer input, which we're going to need to save in a class variable so we can use it during back propagation, that's just the input the layer gets. If we haven't initialized the weights, we initialize the weights based on the shape of the layer input and the number of neurons in this layer, and then we say that we have initialized the weights. And then we get our activation input by just doing the dot of that input in the weight matrix, and we feed that through the activation function. Then the back propagation step is a little messier. So you start out, you get this layer gradient from the layer above you. So if you're the last layer in the neural net, that's your loss. If you're another layer, it's how much the outputs of your layer are affecting the loss. So we get the derivative of the activation output with respect to the input by, if you remember, kind of like we did with the sigmoid function, we looked at the derivative of the sigmoid function with respect to its input. So we're going to feed the activation input through the activation function. Then we're going to multiply that by the layer gradient to get the derivative of the layer gradient with respect to the input. And then, and this is that sort of logic of the linear algebra of where the partial derivative of C with respect to W was B transpose, and the partial derivative of C with respect to B was W transpose. The partial derivative of the activation input with respect to the weights is just the layer input transposed, as it turns out. And then we update our weights. We do the dot product of those two things and update our weights and increase the number of iterations, and then send this output gradient down to the next layer. the backpropagation step. What some people have done to make this a little more intelligible, what someone should probably do and then send me a pull request, is to separate out the activation function and the matrix multiplication as separate layers. But I don't know, to keep things more in line with how we did the neural net from first principles, I wanted to keep it all in one layer here. Anyway. So any activation function you define should have a way to send information forward and backwards. So sigmoid, if you're doing backpropagation, define it as that, sort of recursively, and otherwise just return that. And mean squared error, same you don't do it recursively, but it's the same kind of thing. If you're doing backpropagation, you return that, and otherwise return that.
But you can use any of the class functionality.
Yes, yes. I also go over how to use cross entropy. Not in this 90 minutes, but it's further down in the notebook, in the appendix section. Yeah. All right. So then what does the actual API look like? We could define a neural net just like we did last time this way. We have, if we just wanted one hidden layer, the hidden neurons argument could just be a list of length 1 with 50 neurons. We could have 10 outputs. And this is a neural network just like we defined last time. And then to train it, there's some helper functions here. And let's train that for 1 epoch. I think we can move on while it trains. Does it work? What we'll see is the accuracy, it's the same as last time. I think the accuracy should be about 90% just for training this for 1 epoch. Now we'll, okay, yeah, what is it? 89%. Cool. Now we'll actually get into some tricks. So it works kind of, oh, and actually before we get into the tricks, first I'll show you that this does in fact do deep learning. So you can in fact have multiple hidden layers in this framework without importing Keras or TensorFlow or anything like that. And this can actually learn things like how to predict which digit a handwritten digit is. So this is a neural net with multiple hidden layers. The first hidden layer has 75 neurons. The second hidden layer has 25 neurons. And we got 10 outputs. And there we go. Let's train that. Let's get the accuracy. That's actually going to take longer to train, but you'll have to trust me that the accuracy is 90%. I want to get to some of the cool stuff. And again, I think, so the point here is this only kind of works. 90% is way better than random, and it shows that this neural net is in fact learning, but it's not a great score on MNIST. The top scores on MNIST have less than 1% error. Yeah, what did we get there? 88.6. Yeah, it only kind of works. To get neural nets to learn better, we have to actually do all sorts of tricks. And that's actually part of the fun of deep learning, is trying out things and trying to pull different levers and turn different knobs to see what works better on certain complex problems. So I'll go over, because we're doing this from scratch, I'll go over how to actually implement some of these tricks in this sort of, in these functions that have been built from scratch. And hopefully you'll come away with a little bit of a better understanding of what's actually going on in these tricks. I think we hear about a lot of these things, and you might have heard about something like learning rate momentum and tried values of 0.9 or 0.8 or 0.75 in your model, but not really known what was going on. So the goal here is when you see them actually happening from scratch, you'll have a better understanding of what's actually going on. All right, let's get to as many of these as we can. So first, just learning rate tuning. There's Joshua Bengio. The learning rate is the single most important hyperparameter, and you should always make sure it's tuned. All right, so the learning rate is actually really easy. It's just a number that you multiply the weight update at each step by. Coding this up, all we do is in the setup layers function, well, first in the actual layer itself, we just multiply the weight update by a learning rate. That's easy. I think I might have skipped one. Let me go back real quick. No, I don't think I did. Next, we've got to modify setup layers to give each layer a learning rate. So there's a sort of hacky thing you have to do here, or at least I did, where each neural net has layers as attributes. So in order to change attributes for those layers, you have to use this setAttr function. Because I want to give the neural net the learning rate. I don't want to give each layer the learning rate. So I want to do it this way. All right. And I think most of you know what learning rates are, so I'll sort of go through this one quickly. So, okay. Then we have to change the forward pass function to use the new setup layers. And you can tune the learning rate. And I won't do this, but you can imagine you can write a little helper function that goes through all these different learning rates from 0.1 up to whatever you want, at whatever step size you want, and computes the accuracy of the neural net with these different learning rates. You can do this in TensorFlow or Keras, but it's kind of cool that we're doing, just from code that you've seen in the last hour, we're doing hyperparameter tuning on deep neural nets. So I won't actually run that because it'll run the neural net through many different neural nets with different learning rates, but I found 0.3 in this case to be the best for this architecture and for this problem that I'm using.
Why is the same learning rate for the whole broadcast by layer?
Yeah, that's literally just so I didn't have to, when I was defining each layer, write like learning rate 0.1, learning rate 0.1 over and over again. What I'm about to do right now is varying learning rates by layer. Oh yeah, good point. So his question was just, why wouldn't you just put define the learning rate on each layer as opposed to defining it on the neural net? Okay, this is here's one trick you might not have seen. It's a little less common, but it actually works well when it's implemented. So you can vary learning rates by layer. So why might you want to do this? Well, if you think about what's going on during backpropagation, at each step of backpropagation, we're feeding data backwards through the neural net. And in particular, we're feeding it through activation functions, which are multiplying these gradients that we're sending backwards by, at most, the steepest point of the activation function. In the case of when you're using sigmoid activation functions, or tanh is another example, that means you're multiplying it by a number that's significantly less than 1. In fact, with sigmoid, you're multiplying it by a number that's at most 0.25. So at each point, the gradient's getting multiplied by at most 0.25. So what you might want to do to help your neural net learn better is actually use higher neural nets closer to your input layers and use lower neural nets closer to your lower learning rates closer to your output layers. So how might you do that? What if you wanted to code that up from scratch? All right. Well, we can modify the setup layers function to have this learning rate layer decay parameter. And what does that do? So if that's 10, say, what we'll do is we'll go through all the layers when we're setting them up, and we'll divide the learning rate by the learning rate layer decay raised to some power. So if the learning rate in the first layer is 1, the learning rate in the second layer might be 0.1, then it might be 0.01, etc. And we'll make sure we do it correctly for the last layer as well. That's what we're doing there. And we'll have to modify setup layers there to include the learning rate decay parameter. Define a little new neural net there. And let's run this. With randomly initialized weights, you never know what's going to happen. But in most of the time when I've run this, it's given me better accuracy with using this layer decay. We'll see. 90.4. I think it was at like 88 or 89 before, so probably not significant there. Still, we're seeing how this stuff works. All right, momentum. This is one that I think many people, if you've played around with TensorFlow or Keras, you've tuned a momentum parameter. You might have tried to make it 0.9 or 0.8 or 0.75 or whatever, and you might not know like what's actually going on under the hood there. Like, what does it mean to use learning rate momentum? Well, let's talk about that in detail. So by default, the weights in a neural net are updated according to this equation. We take the weights, we subtract off a learning rate times the partial derivative of the weights with respect to the loss. So this is equivalent to doing gradient descent, essentially, with each weight. I think it's really important, and when I teach at the Metis Data Science Bootcamp, I make the students know the equation that you're subtracting off the partial derivative of the loss with respect to the weights. But you can also think of each weight as existing in, on the x-axis there, and what you're trying to do at each step is figure out whether to increase or decrease it, and you're just trying to go down a hill. And the going down a hill analogy lends you to think about, well, if we've been going in the same direction for multiple iterations, then maybe we should speed up and go even faster. Versus if the weight update increased on one iteration, then decreased on the next iteration, then maybe we should slow down. Maybe we should not just have the weight be jumping all over the place. So what does momentum actually do? If our weight update at each time is u sub t, instead of our weight update at each time step being just u sub t, momentum would be this. It would be u sub t plus some momentum parameter times whatever the weight update was in the last time step, plus the momentum parameter squared times whatever it was 2 time steps ago, etc. So sort of a weighted sum going backwards of what all the weight updates have been. And u is a decay parameter. It's usually something like if you want a lot of momentum, then you could use something like 0.9 or 0.8 or 0.75. If you don't find that momentum is helping in your problem, you could either set it to 0 or set it to 0.1. This is equivalent to and often described as increasing your learning rate when you think your weight updates are going in the right direction, and decreasing your learning rate when you think the opposite is happening. Coding this up actually turns out to be way easier than you might think. So first of all, we have to add a momentum parameter to each layer. That's easy. I'll skip over that. Coding this up, though, is pretty easy, or turns out to be sort of elegant. You don't have to code out this complicated equation. So the way to think about it is at each time step, you sort of have a velocity. You have a amount that what the weight update would be if you just did the normal weight update thing, where you multiply the learning rate by your partial derivative. Yeah, question in the back. Yeah, how do you know how to tune things? I think I'll come back to that at the end or when I'm done with this explanation. That's a just challenging question to answer concisely, but it's a great question. So how do you code this up? What you do is you define your velocity to be whatever the learning rate or whatever the weight update would be if you weren't using momentum. So just multiplying the learning rate times how much the weights change the loss. And what you do is, at each time step, your velocity is the sum of basically what your weight update would be, so that u sub t factor, plus all the prior weight updates. And what are all the prior weight updates? The way to do that is at each time step, you just take your momentum parameter and multiply it by whatever the current velocity is. Whatever the current all the prior weight updates is. And so when you sort of propagate that backwards, that ends up with the equation that we saw on the prior screen. And that's how you do that. And there's nothing really different going on there. And if you run this, I won't run this now, but you can run this and see that this actually works. It can increase your performance if you run this for lots of epochs, et cetera. All right, dropout. Let's, again, just sort of, many of you have heard of dropout. Some of you actually in this room probably understand what dropout actually does and could code it up. But for those of you that don't, let's actually look under the hood and see what it actually does. So dropout is a trick that researchers have found to increase the performance of neural nets in a lot of cases. And the analogy that I often use for explaining dropout is this. Imagine you have a basketball team with 10 players. So only 5 can be on the court at once, but you have 10 on the whole team. During the regular season, you might say, I'm going to, every game, randomly choose 2 players that aren't allowed to play in this game. If you did that, your team would have to not become reliant on particular combinations of players. It would have to learn new ways of working together. It would have to learn new plays. Different people would have to adapt to different positions, et cetera. And that's actually why researchers have found dropout works. It turns out when you don't use dropout, it turns out that the neural net can almost overfit early. A few neurons can sort of learn the pattern that gets you most of the way there in terms of accuracy, but then you never overcome that. And so dropout is a way to get around that. So what does dropout do? Dropout randomly selects a proportion of the neurons at each training step through the network to be set to 0, and just sets them to 0, and doesn't include them in that training pass. Now, in the basketball analogy, when it comes time for the playoffs, you'd actually want your all 10 players available. So with dropout, you don't want to actually include dropout when you're trying to predict using your neural net. This is actually a common mistake you see a lot. And, but yeah, it can often help your neural net train better. Oops. All right, how would you implement this? This is just, oh yeah, here it is down here. So if we have dropout, what do we want to do when we're passing data forward through the neural net? How can we actually implement dropout? Let's say we have a dropout parameter of, the way dropout usually works is if you have a dropout parameter of 0.8, by convention that means you drop 20% of your neurons at each time step. So what would you actually do? If you have dropout in your neural net and you're not predicting, and predict is a argument in the forward pass function, what do you do here? You randomly choose a proportion of the neurons in that layer. The proportion is 1 minus dropout to be set to be your 0 indices. And then you set them equal to 0. Makes sense? So, you know, this stuff that might seem complicated or seem like it's magic going on under the hood, it's not. It's just simple manipulations of matrices and stuff like that. And you can test this, and I actually found sometimes, and I don't have time to run through this live, but using low momentum but dropout of around 0.75, I was able to get this above like 95% accuracy as opposed to 90. But you can run all the cells in this notebook, clone this from GitHub, run all the cells in this notebook. You don't need to have anything other than NumPy and play around with this on your own. All right. So weight initialization. This is another one of these tricks. Yeah?
Question. So on the dropout,
yeah.
What are you propagating? A 0 or the same X?
What you're propagating is, so his question was, what are you actually propagating with dropout? So if you remember in that basic neural net, there were 4 hidden neurons. Those are just 4 numbers you would normally propagate forward. With dropout, you would randomly select one of those numbers, for example, to be set to 0, and then propagate forward the other 3 numbers, but with one of them as 0. Yeah? Actually, the value of the neuron would be set to 0, which is the value of the neural net after things have been passed through the activation function. Yeah, it's a little complicated because in neural nets you have your weights, which are actual things you change, and then you have the values of the neurons that are the result of multiplying weights by images or inputs or data. So you actually take the result of that multiplication and set that equal to 0. Yeah, so her question was, could you do dropout anywhere in the net? Does it have to be in a particular place? You could do it in any layer, and I think another one of your questions was, do you have to do it before or after the activation function, for example, like the A or the B? And the answer there is it actually doesn't matter whether you set things equal to 0 before or after the activation function. But yeah, it's a good question. Yes? I'm sorry?
Instead of dropping out, you can not just say, okay, I'm using the number of neurons because that's the practical second.
Using fewer neurons isn't necessarily the same thing as having a larger number of neurons, but only using half of them on each pass through the neural net. Like having a basketball team with 5 players is different than saying I'm going to have one with 10 players, but only use 5 for every game. Like a randomly chosen set of 5 for every game. I think that's one thing I should make sure I explain. With dropout, you're randomly choosing which neurons you set to 0 at every iteration. So you could choose one set of neurons at one iteration. The next iteration, you choose a totally different set of neurons. The next one, you choose a totally different set of neurons. I think that might have been your question. I'm sorry? Yeah, it means one batch of data being fed through the network, yeah. It's not, an epoch would be feeding the whole data set through the network. So like one data point through the network, what we did earlier, that would be an iteration. An epoch would be doing that 8 times and feeding all the data points through. Yeah, there's a lot of terminology with this stuff, which is why I think it's important to like try to demystify it sometimes. All right, weight initial. So I'll do 2 more tricks, and that's all I've got. I've got two more little tricks. So weight initialization, that's another area of research in neural nets. How should you initialize your weights? Here I just sort of naively chose them from a normal distribution. Not necessarily the best way to do things, just a naive way to get a prototype of this working. There's some research that suggests, basically, if you think about it, the amount of data that's going into the next layer is there's n neurons going into each one of the features in the next layer. So in order to keep the variance of what's being sent to the next layer roughly equal, a best practice that's emerged is to have the variables, the weights drawn from a normal distribution, but the variance in that normal distribution is 1 over the number of neurons in that layer. So if you have a ton of neurons in that layer, the weights, you want to have less variance for each neuron, so that the variance when you multiply those neurons by all the weights ends up being roughly the same. And that, for some reason, I don't really know why, is called, I don't know how to pronounce that, Javier weight initialization. And how do you implement that? You just do that. For each layer, you scale the normal distribution by 1 divided by the scale, in this case, means standard deviation, and you ultimately want the variance to be 1 over n. So you scale it by 1 divided by the square root of the number of neurons. All right. And we'll change setup layers, so we add that to each layer, and we can test, you can go ahead and test that out. The last one, and this is kind of cool, this is a technique called drop connect. And this is the advantage of coding these things from scratch. You can play around with techniques like this. This is a technique that was used in what so far was actually a paper published in 2013, so 4 years ago, which is a long time in neural net research, but is still the top result on MNIST. It's still like the technique that it was, Jan LeCun was one of the authors, and it's still one of the techniques, it's still the technique that's gotten the top result in terms of accuracy on the MNIST data. And it's not in TensorFlow. There's a hacky way you can implement it in TensorFlow, but it's not implemented for whatever reason in some of the most common neural net libraries. My guess is it's because TensorFlow isn't actually just coding up equations like I am under the hood. They're defining a graph, and so my guess is Drop Connect would break that. Oh, by the way, I didn't go into what is Drop Connect. Drop Connect, so dropout is you set a proportion of the neurons of a network to 0. Drop Connect is actually, you just randomly choose a proportion of the weights on each pass through the network and set them to 0. It's as simple as that. It works, or at least was hypothesized to work, for the same reason that dropout works. And it's used successfully in the case of, like, it's still the state of the art in terms of classifying MNIST digits, but yeah, it just never caught on for some reason. But yeah.
What's the significance of that? I understand by dropping the neuron is just like a load testing neural net, especially that it doesn't use space. One of the neurons is not giving any output.
Uh-huh.
What is the concept of dropping the weights?
Yeah. I think it works it's hypothesized to work for the same reason that dropout is hypothesized to work, in that there are probably certain weights that on early passes of a neural net will learn almost too much information. And so setting those to 0 on some of the passes will cause the neural net to learn redundant representations of the data. Yeah, I think for some of this stuff, the answer as to why it works, I think we're like, we as a neural net researchers are like far away from coming up with great explanations to that. Really? Yeah. Okay. I like that people are actually running this live. This is awesome. It runs for a long time, right? Drop Connect? Yeah, it takes a long time. Well, we can chat after this. There's a lot of knobs you can tune, so you have to make sure you're tuning them in the right way. Yeah, question there in the back. Yeah, could be. The gentleman in the back said that. Yeah, sure. So we were hypothesizing over here, why might drop connect work or dropout not work or vice versa? And this guy in the back was saying that it could be because, an analogy that could explain why dropout works is like if the neurons are servers and the connections between them are like internet connections, then he's nodding his head. I honestly don't think I fully understood the explanation, but yeah, he gave me a thumbs up, so we're good to go. Yeah?
It seems to me that like each node is basically a combination, so if you're doing that, you're dropping a lot of information, whereas if you're dropping out a single connection,
Yeah.
you're forcing the network.
I think, so overall what I'd say is researchers don't fully understand why tuning certain knobs in certain ways works for one data set versus not working for another. It's more like, an analogy I heard recently was that we discovered fire years before we knew any of the science as to why fire worked. Like humans figured out that rubbing two sticks together made fire way before we figured out that, we understood any of the science as to why that worked. So I think we're a little bit in that phase right now with neural nets. We figured out that these things can sort of do this thing that mimics learning based on these really basic mathematical concepts and just feeding a lot of data through these algorithms through brute force. And we don't fully understand why. We can come up with explanations, but that's about all. What I'm going to do is I'm basically almost done, so I'm going to wrap up, and then I'll stick around till 5:15 as late as people want to stay for questions. This is basically how you could apply drop connect to a set of weights. To do this, you sort of have to reshape the weights to get certain weights set to 0 and certain ones not, and you have to make sure you do that in the right way. But I'll let you go ahead and look at how that's done. Looks like some people are successfully running the code and actually testing this, which is awesome. And what do you have to do? You have to apply drop connect to each layer to get this to work. And in the forward pass, you just have to make sure that you don't apply drop connect when you're predicting. That's really all that's doing. And you can test that out there. And that's all I've got. So thanks so much for sticking